Yes.
Thank you. Welcome back to the class. So today we will continue our discussion on now spatial models, spatial population models, specifically reaction diffusion models. Okay. So let's sort of recap what we had done in the previous couple of classes. So we have been looking at a model of this type, right? Where n depends on both x and t, right? And then you have f that depends on n, and then we have a diffusion term. Okay, and then we did some numerical experiments, right? And I asked you to do some, and I showed you some numerical experiments, and we discussed the idea of equilibrium. We will discuss the idea of stability. So we discussed the idea of homogeneous equilibrium. Right, where basically you start with all the mean field values, right? At all points for at x. Okay. So and then using both numerical simulations and analytical calculations, we showed how the stability basically remains unaltered, right? With diffusion, okay. And then specifically, I had asked you a lab assignment last time where I had asked you to look at the bistable region. So this is the harvesting parameter H. This is the mean field equilibrium, and we know that this looks like this. So for those of you who are not in EC 101, you really need to revise this on your own. Okay. If you don't know, let me know. I can sort of just put some references for this, but all the video lectures must be there from the previous course. Okay. So the equilibrium structure looks like this. So there is this range of values of H for which we have bistability, right? Bistable ecosystem. And of course, H equal to 0 corresponds to the logistic model. That sort of standard logistic model, continuous standard logistic model. And here I showed that this is unstable, right? The origin is unstable, whereas this would be a stable equilibrium. Okay, so any smallest perturbation you make in space, makes the system flow towards the carrying capacity equilibrium, homogeneous carrying capacity equilibrium. Which means even if the entire space was extinct, a small perturbation anywhere you make in the space gives rise to this. And that will continue to be true in this range up to this value. Let's denote this by HC1 and let's call this HC2. Between 0 and HC1, I had asked you in the last class, to find out what happens, is this feature true across the entire spectrum? Specifically, I had asked you to look at the bistable region. So what you should have found is in this region between 0 and HC1, this simple idea of a smallest perturbation from 0 leading to flow towards the carrying capacity equilibrium must hold true throughout this. Of course, it won't be exactly carrying capacity in this region, slightly below the carrying capacity. Okay. Now, in this region, what do you expect? A small perturbation you do will typically flow towards this lower branch. This is what you must have found. But here is the thing, right? We do know that in this parameter regime, in the mean field model, if I had made a large enough perturbation, for example, think of the mean field model, and if the perturbation was here, what do we expect to happen in that case? If the initial value of the population density was above this dotted line, then it would have actually flown in this direction, right? The question is, what happens? What happens in the case of the spatially explicit model? So I had asked you this question to figure out by numerical simulations. I will just quickly show you, from the code I had given you what happens. Okay. Just in case any of you had any questions and confusion. Okay. So I'm sharing you this R code. Are you able to see this? Okay. So it's the same code. I have made one small modification in the code, and that is done in the initialized space function. What I have now done is I have introduced a perturbation, which is basically a patch of size A by A, a square grid of the size A by A, located at roughly the center of this patch. So since the system size we were using was 50 by 50, I have roughly centered it around 25. In fact, a better thing for me to do is, let's say AC standing for center. Let's actually say C. Okay, this would be a slightly better way of coding it. Okay. So around XC, we place a patch of size A. Okay, so that's what this part of the code does. Okay, and so A could be any number. Of course, it should not be more than the system size. Let's say A is equal to 1. So, and what this code now will do is exactly at one location. In fact, in this case, 2 by 2 locations. It will place a perturbation which is a carrying capacity equivalent in those grids. Okay, so let's see what happens if I run this. So you can see that there was a 2 by 2 square grid. I just realized that the way I have written code, even when I say A, it actually makes it A plus 1. So I just change the code. And now A means A by A. Okay. So I have now placed at just one location, but the strength of perturbation was pretty high. I had placed a strength of perturbation is equal to carrying capacity, but doing it at one location is insufficient. As you could see, that patch has now died off. But what's really happening is that from 0, the system will actually go to the lower stable state, not the upper stable state. So if we just wait up for long enough, from the dark blue, which was at 0, we will probably flow towards somewhere around 1 or 2, which corresponds to the lower branch of the equilibrium in the harvesting model. Okay. Of course, I should tell you that I have chosen a value of H is equal to 2 here, which is sort of right at the bang of somewhere roughly in the middle of the bistable region. Okay. So what this basically means that just because I made a large perturbation, if it doesn't mean that it will go to the alternative stable state, the upper branch. Okay, so what do you need to do? So let us increase the patch size at the center. Let's make it 2 by 2 now. No, it's not completed. Okay, now it's running. 2 by 2 is running. You can see there was an initial patch of 2 by 2. Even that seems to be dissipating out. The 2 by 2, so in 4 grids, I have placed density of is equal to carrying capacity K, but they all seem to be died down quickly. And then what will now happen is the entire system will go towards the lower branch, which is around 2, I think, somewhere between 1 and 2. Okay. So if you run this long enough, we will know. So we'll stop here though. Let's do 3 by 3. What happens if I do 3 by 3? Will the result be same? Again, yeah, it looks like it has dissipated. It is dying off. Okay. So it's going towards the lower equilibrium again. There is a diffusion from the center. Again, the entire system will reach the lower equilibrium. Is that right? So even 3 by 2 dies off. Okay. Let us see what happens with 4 by 4. I'm going to stop the simulation now. Now this is 4 by 4. it looks like even this dissipated, right? So again, they're all using this, this bluish color here. And again, you expect that from the 0, they will just go to the lower branch. Okay, so things, as you can see, although I have made a large perturbation and I'm making in various sizes, they're all not taking to the upper alternative stable state, but they're all coming to the lower alternative stable state. Lower density. Let's make it maybe 10 by 10. Let me jump across. Let's make it 10 by 10. See, it's a huge perturbation now. The strength of perturbation at each pixel or each location is same, but the area is now huge. What happens now? Do you think it died down?
It's growing.
It's growing, right? So, so what? So is it the lower branch it is growing? Is the upper branch it is growing now? So look at the red colors are roughly
Upper
on.
branch.
So it's close to 7 and 8. Yeah, right. No, so the upper, it seems that in the center, what you now have is a patch of the upper stable state, the higher vegetation density, higher population density stable state. Okay. Okay, I just have to wait long enough. I can clearly see the at the center, the color is becoming denser, redder, which means the density is going up in the middle. Not only that, this area, right, this circular patch of high density is also increasing. So now there is really a diffusion of the upper density, higher density branch across the entire space. If you wait long enough, you will find that it will take over entirely. Okay. So what can you infer from the simple simulations I have shown?
So the area of perturbation also matters, not just the strength of it.
Exactly. Okay. What else? Absolutely. What else can you say about the area?
And should it be greater than the unstable line is there in between, right? So
Okay.
okay. So does it have a relation with that?
What do you think?
Oh.
So I'll share that back. I'll share this back now. What do you think? See, you remember that all the perturbations I was making had value of k. So this was k. So all the perturbations had the value of k, right? Only the area was changing. So how does it relate to this now? How does it relate to this?
Is it like the total perturbation by total area or something?
Okay. So basically, you just add up total perturbation is n, a square of the number of pixels, right? So a square into k is the total perturbation, and divide by the total number of number of sites. That's one way to think about it. I'm not sure what you will get from that. Okay. I think the answer is related to what you are saying, but not precisely. I will tell you what happens. Now let me make you do a guesswork here. So first and foremost, I'm expecting one more comment from you. So here are our observations, right? From the numerical simulations in the bistable region. First is small patches of perturbations. What do they happen? They die out, right? Second observation was large patches can grow. From these two, what can you conclude about the area of patches and whether the perturbation grows or decays? Do you agree with the statement? And above which that patch expands. Do you agree with this statement?
Yes, sir.
These two observations, is this a reasonable inference to make? Okay, so there is a critical area of the patch size. Okay, I think area of patch is sufficient. I don't have to say area of patch size. There's a critical area of patch. Let's call that, AC. Okay, below which the patch decays and above which the patch expands. Okay. Okay. So now let me ask you this question. So I showed you one simulation where I had, for this value h is equal to 2, I showed you these two features. So if you were to do these simulations and again, you will find AC. So what's the value of AC going to be for the specific values I had chosen? We knew it had to be less than 10, right? Because 10 is or equal to 10 because 10 grew. It had to be greater than 4 because we knew that the 4 by 4 decayed, right? There's some value of AC that is, that's there for h is equal to 2. Let us say if I plot AC as a function of h, how would this look like? Okay, I'm hoping you can see both the graphs now. If I were to plot AC as a function of h, how would this look like? Let's say this is h C1, this is h C2. Okay, so of course, what is AC? How are we defining AC? We are starting with an initial condition of bare state. Okay, and then I'm introducing AC, a patch size, all of which have values equal to k. Okay, now with this, how do you think AC will change as a function of h? Can you all make a guess? Can one of you make a guess and tell me?
Should it be non-zero in the region between HC1 and HC2, and then
Okay.
zero
So
in the
it
rest?
will reduce or it will increase with it, this way. Will the minimum size required increase or decrease? So it's right, it's non-zero between these two, but will it increase? Is this going to happen or is it going to be this?
It would increase.
Increase. The minimum area required will increase as we go towards this point. So we have a very small area that can push you. As you're growing here, increasing here, the area becomes larger. Okay, so think about that. I don't need an answer.
Sir, I feel it would depend on the relative difference between the two stable states and how.
Excellent, no problem. So what I will do is I'll make it an assignment question. Okay, this will be an assignment number 2. What I will ask you to do, I will write down very clearly. I will ask you to do 2 things. So AC, assuming you start with a bare state. Okay, and then how does AC depend on H? And then what is the inverse question? What is the sort of converse or inverse question starting with this? So one, we want to know how much does it take to go from this state to that state, right? Conversely, we can ask, if I am in this state, one can also ask the following question. If there was think of a scenario where people sort of, cut down forest or, destroy an ecosystem. Okay. Some patch of the ecosystem has been destroyed. Okay. Let's say you're somewhere here. what's the area of destruction it can sustain? We can ask the same question, right? So then the AC will be from starting from here. What's the value of AC above which we will actually transition to a lower state? Okay, so I'm going to ask these two questions as part of the assignment. But for today's class, I just hope that in the previous lab assignment, you understood the concept of the critical area of patch that is required to induce a transition from one state to another state. Is this point clear? This is what I was expecting in the previous lab assignment work. Okay, any questions on this?
Sir, so when I try the assignment one, so how I introduce
Not the
perturbation.
assignment, sorry. Not the assignment, the lab.
Yeah, sorry, the homework.
Yeah.
So they're introducing perturbations. Other than the strength of perturbation, the other thing I had done was increasing the randomness. So I had chosen the pixels randomly to give perturbations. So in that, what I
Spatially
observed was,
randomly spread, is it?
yeah, so if I chose more pixels to perturb, then I found the whatever observation you were saying
Yeah.
corresponding to larger areas.
Fair enough.
But in that sense, can I really relate to the total area that I'm perturbing, or is it sort of the density of pixels that I'm perturbed?
That's
in
a
that
very
case?
interesting question. So think about the following. Say you have this landscape, okay? Let's say they're all in the lower branch, or in the extinction state, okay? There are two things I can do. Yes, let's call this S1 scenario 1, the one that I was just showing, which is introduce a area A where everybody is at carrying capacity K. That's one thing I can do. The second scenario you can do, which is exactly what we have done. What's your name, by the way? Okay, but this is not an area. Okay, you have spread out all over the place. No, so instead of a patch like this of size A, what you have is spread out log. So let us say that A is equal to A squared by A squared. Oh, sorry, not A squared by A squared, it's A by A. Whereas you have actually, let us say, randomly chosen A squared cells, randomly chosen. Now, answer me the following question: which of them will have a lower value of AC?
I think the S1 will have.
S1, no, exactly,
Yeah.
because it's a concentrated area, right? So because one can think of, let's say I have found an AC from this scenario, okay? S1 has scenario AC, right? Now, unless each of this is greater than AC, what will happen? Each of them will basically decay, right? So it's of course possible that when A square is sufficiently large, the randomly placed one can also be a cluster. Okay. And there might be another cluster here. And maybe before that each independent cluster decays, they may actually fuse and make a cluster bigger than AC, and then they may grow. But
Yeah, that's what I observed. So,
Yeah.
so in that sense, for the randomly scattered perturbations, more than the area itself, it's somewhat dependent also the total space that we were perturbing A square mini cells, right? If I was choosing A square mini cells in a larger area, then it would be difficult for the patches to grow.
Yeah, anyway, let's assume we have fixed the system size as n by n,
Sir?
whatever the fixed size is. Okay.
Sir?
Go ahead. Yeah.
Sir, I noticed one more thing. So when we have like a small contiguous area, like an S1, I think this is because of the way we have defined the diffusion equation. It depends on just the 3 cells adjacent to the cell, or the small cube around the cell itself. So I found that it is directly dependent on diffusion coefficient, however big the area is, because even if we concentrate it wouldn't be able to spill over if the boundary is not allowing it.
Yeah, absolutely true. Yeah. So, basically, what's the relationship between? You can ask the following question now, right? We know numerically that there is some AC, right, for a given set of parameters. How does AC depend on, right? One is H. When I say H, what I really mean is, the specific location in the bistable region, right? It depends on H, right? It depends on what else? It depends on the diffusion constant, right? because diffusion constant determines the rate of spread. So how do these two? And then second, another thing it depends on will be the geometry that it shows. So all these three things actually determine the value of AC. Imagine I had, instead of a circular filling, I have chosen a square, or I could have chosen something like a ring, right? I could have also chosen a ring of the same area. So the geometry also matters. Okay, so all these factors do matter whether that patch actually grows or not. Okay, and usually, for all the analytical calculations, we focus on a circular sort of area. Okay, and this is also a fairly, there is an important area in physics called the idea of domain growth. Where if there are various there is a material, and if you introduce a domain of the opposite phase inside a material, what happens to the domain? Is it going to decay? Is it going to expand? And that's an interesting question that physicists study, and what we are studying actually closely relates to that problem of domain growth in condensed matter physics. Of course, the one fundamental difference between a physics system and the one that we have written is that in physics you address all these questions with ideas of free energy, okay, temperature, which include, of course, free energy includes temperature, entropy, and also surface tension. Okay, now some of these ideas can translate to what we study here also, but of course they don't mean the exact same things. So especially the idea of surface tension actually also holds true here, except that the typical physical meaning you give apart from the geometry doesn't fully translate. Okay, so so what I will do is there is a simple analytical calculation we can do to sort of to actually see what is AC, what's the minimum area of domain that is required to expand. I can actually share the analytical calculation, canvas sometime soon. Any question? Someone seems to have accidentally switched on the mic. I think Paris.
Sorry.
Thank you. Okay. So this is about critical path size. In fact, there is evidence now that these type of critical path sizes are indeed relevant in ecological contexts, in preserving ecosystems, and in introducing alternative sort of if you want to sort of restore an ecosystem, right, a degraded ecosystem. Okay, these ideas do become important. Let me just tell you an interesting story that happened within the context of this course itself. In 2014, I taught the exact same concept along with analytical calculations, which I am not doing this year, by the way. I'll just share you the notes. And there was one student back then who actually learned this concept, and then he sort of made some additional improvements to the calculation to make them a lot more applicable to ecological contexts. Okay, so let me just share you one interesting and then he continued to work on this for his master's thesis when he went to for a master's thesis. So the physics student, his name was Nikunj Goel. So he actually then published a paper, a very, very interesting paper that connects this kind of a reaction diffusion equation model, and he made some prediction on how dispersal, which is modeled by diffusion equation, influences resilience of savanna and forest distributions. And with this paper, he went on to actually win a number of awards. For example, last year he won Best Theoretical Ecology paper from Ecological Society of America, and previously he had won Best Presentation also from Ecological Society of America based on the work that he presented in one of the meetings. Okay. So, the main point, in fact, this is a paper where the mathematical techniques covered aren't too fancy, and with what you have learned now, you must be able to even understand a paper like this. So okay, I thought that was an interesting incident that happened, that happened within the course, a research project that came out of this course, and also was a very interesting piece of work, which I was also quite lucky to be involved in. Okay. Okay, cool. That was the sort of brief note I wanted to share about critical path size about the previous lab assignment. So, any questions before I move forward?
I have one. So in the last class, we derived the local stability. We done something related to local stability analysis, right?
Yes.
So here, how do we define the local stability? So in one dimension or in just OD case, we say that the perturbation should be small enough.
Mhm.
So in this reaction diffusion case, we have two things, right? There is a strength of perturbation and there is the path size. So when we say locally, it should be small. So
Okay.
how do we define it then?
1 second. So yeah, that's precisely okay. This is a good question you asked. So now let me just try to maybe explain that. Stability analysis for reaction diffusion equation, right? So let's just recap what we learned. So we had a general form of the equation like this, right? This was the equation we had. So in the mean field, how did we define local stability analysis? So local stability criterion was that f prime and star was less than 0, right? Okay, now what does this mean? It means that in the Taylor series, n star plus n, right? In this Taylor series expansion, okay, so first term anyway becomes 0, f of n star, right? And second term will be this, right? F prime of n star. And then the third term will be f double prime n star, right? And then you have higher order terms. So what does local stability analysis mean? Of course, this is 0 anyway. Local stability analysis means that I'm going to ignore all these terms. Okay. So n is sufficiently small, implies I'm going to ignore all these terms. Is that fine? And this is usually true when f double prime n star is non-zero. Okay. So the criteria is that this is the criteria that we had for the mean field local stability. Now, what about stability for spatial system? For reaction diffusion equation, remember what we did? We again considered nx of t is equal to n star mean field equilibrium plus a spatially dependent small perturbation. Okay, and then what we did was we wrote down the following, right? So we found the, so if you do the, again, local stability analysis, this is what you end up with. This is approximately equal to alpha times f prime of n star, right, plus d del square of n. Okay, so this is true, or true rather than true, this is valid, right? Again under the same conditions, right? So to arrive at this, we actually do the exact same, exact same Taylor series expansion of f. So okay, I'm sorry, I missed the term n here. Also n here. So valid diff, if we can ignore n squared, which now depends on x and t, f double prime n star plus other terms, if these can be ignored. Yeah, this is the condition when linear stability analysis is valid. This is the mathematical condition when it's valid. So it's exactly the same condition really, except that now n is also spatially dependent.
Okay.
Any other questions? Okay, so if there are no questions, we will move on. We'll move on and now to coupled populations with diffusion. Okay, so I already introduced the model to you, the general model. Okay, so let's write that again. The partial derivative of species 1 of the population 1 will be given by some f n1 n2 plus del square n1 with the corresponding diffusion coefficient d1. So we also have a second population and the corresponding diffusion equation. Okay, so now we have a coupled population dynamics, both of which are diffusing in space. Okay, so so we asked the following question in the context of one species, right? We know that in the one species context, a locally stable equilibrium, a homogeneous equilibrium, continues to remain stable even for heterogeneous perturbations. We derived and proved this using the idea of Fourier transforms. Were you all comfortable with the derivation we did on Monday? Were there any doubts, questions? The basic principle there was I can introduce a perturbation which can be written as summation of various sines and cosines. And we took only one such perturbation, one periodic perturbation, and we showed that for all values of the periodicity of the perturbation, the system was continued to be stable if it was homogeneous. It was the mean field system was stable. Okay, so which means that even for heterogeneous perturbations, the system was stable. The reaction diffusion system was stable. Now we can ask the same question. Okay, so let's let n star given by n1 star comma n2 star be a stable equilibrium of the mean field system. Okay, so the question we now ask is the mean field homogeneous equilibrium stable to heterogeneous perturbations? If we show that, then we can conclude that the same equilibrium is not only an equilibrium, but also stable for the reaction diffusion equation. Is the question well posed? Is the question clear to everyone? Of course, I have skipped a whole bunch of steps here, intuitive steps. If n star is the mean field equilibrium, right? Then if we consider the homogeneous mean field equilibrium, are you now convinced that that is also an equilibrium of the reaction diffusion system? if I just take the homogeneous equilibrium, meaning, you know, every grid point in the space has N1 star N2 star, will that be an equilibrium of this reaction diffusion system? It must be, right? Because F and G will be equal to 0. So therefore, and then the diffusion term will just go away. Okay. So therefore, it must be stable. Okay. So now to address this question, you know, I want you to work on this entirely on your own today. Okay. I think it's a slightly tedious calculation, but I trust, I will sort of assure you that you will in the end be happy. Okay, let me see if my claim is correct. Okay, so I want you to, because, you know, I think it really shows how, you know, how we can now apply what you learned in the previous class to this slightly more complex system. So will you now go step by step and try to find and prove that the homogeneous equilibrium is stable to heterogeneous perturbations? Okay, so to make life easy, I will give you step by step to go forward. Okay, and then therefore, and then I will you know, discuss once in half an hour or approximately that much amount of time on how you are doing. I'll get you all back into the class. So you go, you know, and then we go back again, and, you know, hopefully by the end of the class today, we will have figured out answer to this question. Okay, that's the game plan for today. So I will now give you some detailed instruction, step-by-step instructions, what you need to do. Okay. So the first thing is, first step is write down conditions for mean field stability for the above model. I have already given you answer to this question in the previous class. Okay, so this is just to make sure you're all on the same page. So let us define the Jacobian. Okay, Jacobian can be defined in the following way. You know, A, B, C, D. Okay, where A is the A and B are all corresponding derivatives. Oops, something happened. Where A is equal to derivative of f with respect to n1, B is equal to derivative of f with respect to n2, C is equal to derivative of f with respect to n1, or it is G. I think in the previous class I wrote f1 and f2, and this class I'm writing f and G. Okay, so, but you must feel comfortable with my notation changes. Okay. So in terms of the Jacobian elements A, B, C, D, I would like you to write down, okay, what are all the conditions for stability. That's the first thing you will do when you go to the room. Conditions for stability. Okay. The second thing you do is, okay, write linearized reaction diffusion equations around the equilibrium. Do you understand what it means? What I basically mean is, remember we had this, right? When we had a single equation, we had this. Oh no. Alpha times n plus d del square n. So what is the corresponding equation of this type when you have the two variables? Okay, where alpha was dou f by alpha was basically f prime of n star. So what would be the linearized reaction diffusion equation around the equilibrium? Analogous to this, but for the This one. So the second step we will do. What the third step we will do? Having written that down, introduce the heterogeneous perturbation. Okay. So this is analogous to what we did in the previous class, analogous to n is equal to I could have chosen, you could choose sine or cosine, it doesn't really matter. Just choose cosine for the analogous to this. Okay. So we had done this kind of a perturbation last time for one variable. Now you will have two variables. So how will you introduce a perturbation and then simplify? Fourth step is simplify. Okay, is this clear to everyone? Simplify to obtain analogous to. So last time we found something like this, ak dot is equal to minus alpha ak, or I think maybe just alpha ak plus, I think we had a term like this. I made it so bad. Minus d k square ak. So we found an equation of this type previously. So I want to know what would be the analogous when you now have two variables. Okay. So this is the first. There are more steps you need to do, but I would like you to go through these 4 steps in your group discussion today. Is that fine? Any questions? And then I will give you more steps once you finish the 4 steps. Any questions before I move you all to your respective rooms? And then maybe by 3:30, it's 2:56 now. Do you think half an hour is sufficient for these 4? Or is it too short? I can decide by when I'm going through, I will take a look and decide. Okay. So roughly around 3:30 also, I will get you all back and try to homogenize your progress. Okay. Any questions before I move you to the breakout rooms? So work this out on paper and pen, because, or if any of you have a stylus and a pad, you can also use that, and one of you can write, others can see and discuss, contribute to the discussions. Okay, I'm going to stop sharing and I'm going to open the breakout rooms now. I'm opening all the rooms, so please start the work. If you have any questions, you can stay back and ask me. Hello, people. This was a mistake. Just I accidentally clicked the close breakout rooms button, and there is no way to undo it. It didn't even ask me confirm. So unfortunately, we all lost 2 minutes. So once everybody comes back, I will put you back in the same room again. Hello everyone, really sorry about this. I accidentally pressed close the breakout rooms, and then it just does without even asking me to confirm. So this happened. So I'll open the breakout rooms again. Really sorry about this. Hello everyone, welcome back. So let me let's all get to the same page now. Okay. So I asked you 4 steps. I asked you to do 4 steps. Let me try to let me try to provide answers for all the 4 steps. And there is, of course, this simplification. I was expecting you to do only 1 step of the process. So I will tell you what next to do once we do this. Okay. Okay. So what did I for the first part? It's this. Just 1 second. Okay, so the first clarification I must tell you is all these derivatives were computed at n star. Okay, so likewise for all of them, all the 4 derivatives were computed at n star, which is the equilibrium. Okay, so now as you do know, as I in fact told you last time, for the first one, once you have a Jacobian matrix, so the condition for the stability of the equilibrium is that both the eigenvalues are less than 0, right? Now, in terms of matrix, we know that the trace of a matrix is summation of eigenvalues, and since both the eigenvalues are less than 0, the trace must be less than 0. This is the condition number 1. And then, since both the eigenvalues are negative, as we also know, the determinant is the product of eigenvalues. So therefore, this has to be positive. So what is the determinant for a 2 by 2 matrix? It's basically AD minus BC. This must be greater than 0. Okay. These are the 2 conditions about ABCD that we need to carry forward to understand the spatial system. So it's the step 1. Is everybody on with me on this step 1? Does anyone have doubts about step 1?
Sir, can you go over the part where you said the eigenvalue is less than 0?
So, this is something we covered in EC 201 for a 2 coupled population system. If any stable equilibrium must satisfy this condition, which is that the eigenvalues of the Jacobian matrix must be all negative. But the more precise statement is the real value of each of the eigenvalues must be negative. Okay. So if the eigenvalues are lambda 1 and then lambda 2, they both must be less than 0. Lambda 1 comma lambda 2, they both must be less than 0. And since the trace is nothing but summation of eigenvalues, the A plus D must be less than 0, and likewise for the determinant. Okay. Any other questions? Okay. So second step, would you like me to derive this, or shall I just write the final answer? So what you need to do now is, now remember that we have now 2 equations, right? N1 and N2, right? So you now need to write down the perturbation is in the following form. Okay, so N1 is equal to N1 star plus a homogeneous equilibrium plus the perturbation which depends on space and time. Okay, time t is equal to 0. I have set, it's only N1, but then it varies with time. And then N2 star times a similar perturbation around the N2, for the second population, a similar perturbation N2. Okay, so you input these 2 in the, of course, when you have input this without the spatial dependence, that's how you get the Jacobian matrix. Okay, now with the diffusion, what you basically get is that, we'll have 2 coupled reaction diffusion equations. I will just write that down here. So the linearized So if you basically apply the same principles, you will find that dou n1 by dou t must be equal to a n1 plus b n2 plus d1 del square n1 dou n2 by dou t is equal to cn1 plus dn2 plus d2 del square n1. So this is the step 2.
So is it N2 in the second step, diffusion?
Yeah, absolutely. Yes, yes. Thank you. Okay. Now, is there anything about this step that would you like me to elaborate? So this is basically the entire same linearization process that we do for the mean field model, but with these additional terms of diffusion. If you apply the same principles, exactly same step apply for these terms, nothing will change there. And these two will just hang around. Okay. So the algebra is identical with the extra two terms. That's all. So nothing really will change. If you are unable to get, it's totally fine. Just go back home and you should be able to derive this. So I'm not expecting that you submit this as the entire steps. I don't expect that you submit as a part of the assignment today. Even if you write down, so even for this, I just want to write the conditions. I don't need you to go through the entire process. Okay. Given the Jacobian matrix, what are the conditions? Just have to write this down. Okay. And what are the linearized RDs? You can just write this down without just, I don't need the entire derivation. Okay. So if you write this down, it's good enough for the submission today, which I have anyway given you. Okay.
Sir, I have a doubt here.
Sure.
When you write an1 plus bn2, we are getting this from the derivation of n1, and where we substitute n1 as with the perturbation. If the function f itself has, let's say, n1 and n2 multiplied, then this would not still hold as an1 plus bn2, right?
What do you mean?
So the function f, so when we write the perturbations as adding an1 plus bn2, wouldn't it depend on the form of the function f n1 too?
No, it doesn't. No, it only because a itself depends on f anyway.
Okay.
So I think you should just need to revise, I mean, I don't know if I don't remember precisely if I did the entire derivation in my previous class. For the mean field model, maybe I can just point to the video, look at the video and apply this to the reaction diffusion equation.
Okay, sir. Yeah.
If not, what I will do is I will provide you the right reference from Strogatz, who will do for the mean field model, but apply the same principles for the reaction diffusion equation. Okay.
I have one doubt.
I can. Yeah, sure.
For this stability, is it required that this should be a predator-prey model?
Not at all. It could be a competition model too.
Okay.
Because this is general, no, F and G are general. They are predator-prey. This is any two coupled system.
I'm just confused. Like C and B, one of the C and B should be they should be opposite signs, right?
Why should they be opposite signs?
No, for the determinant to be positive.
So you have A plus D is negative. There are two ways this can happen. Both of them are negative. Okay. Yeah. This can be true. Okay. The other one is one of them is largely negative. Other one is partially positive, small positive. Then also. Okay. But it is true that one of them has to be negative. But it doesn't mean that both one is positive, one is negative. At least at this stage, there's a thing of that type. No.
Okay.
At the mean field level, that's not required. Okay. Is it fine?
Yeah, it's fine.
Okay, that's about second step. Now the third step. This is where things get slightly more difficult and your application skills become important. Okay, now step 3. So in the one population system, what did we do? We just did the simple thing, which is that of that n is equal to some ak. I'm considering the kth perturbation times cosine kx. Okay. I can define k as n pi by l. Okay, just to make. And I don't want to carry this pi by l all around. Let's define k is equal to n pi by l. So kth mode perturbation can be given by this. Is that fine? That's what we did, right? And then with that, we got this expression. Okay, so now we have two populations, N1 and N2. So let's write the N1 as AK times cosine kx and N2 as BK times cosine kx. Okay, so the perturbation is same mode for both N1 and N2, but the amplitudes can be different. Is that fine? So this is this was one key innovation you had to do in your step 3. So you how do I write down two perturbations now? You can of course write AK for both, except that just couples you down, right? You don't have room to independently perturb them anymore if you assume both of them are AK. So what I have basically done is I've assumed that N1 perturbation has an amplitude AK, whereas N2 has an amplitude BK. But I have chosen the exact same periodicity for both. This was the first key thing you had to think and implement when you are
Sir,
introducing.
yeah, sir, in this, how do you know that the both in N1 and N2, both the K modes will couple in the differential equation? Why cannot the K and L?
What do you mean? Say that again.
Okay, so this is an assumption that
Yes, I partly answered your question by this. This is an assumption, but I encourage you to do what if we had chosen a different mode for N2. Okay. I know it's an optional exercise that you should try. Let's say N2 is B, let's call it M cosine mx. Okay, try this out. Oh, by the way, there's a problem with my horrible notation. I've already chosen A, B, C, D. Let's not call them A and B. Okay, let me call them P and Q. Okay, is that fine? Okay, so I have introduced this periodic perturbations. Now that was step 3. Just writing this down. What's a step 4? You just have to substitute this. Substitute this and then basically in this equation. Okay, I will do that now. What will be the left-hand side for the, so I'll have cosine kx dpk by dt, because p can depend on time, right? So whereas x dependence comes from this term, time dependence comes from the amplitude term. Okay, the first term is a, coefficient a times this. So a pk cosine kx. Second term is p. Here is q now. Okay, b qk cosine kx because it's n2, and then you have a diffusion term applied to n1, d1 del square n1. You remember what happens when you apply the double derivative to a cosine function? This constant comes out with a square and a negative sign. What you have is minus d1 k square cosine kx, and the amplitude remains same, pk. Is that fine, everyone? This is the equation. So basically the the dn1 by dt equation is now replaced by this equation. Is that fine, everyone? Okay, so likewise we can write a second equation which will also have the cosine kx on the back, d qk by dt, that is equal to c, again pk cosine kx plus d qk cosine kx minus d2 k square cosine kx times qk. Is that right? Is that fine, everyone? Okay, what will I do now? I'll just cancel the cosines everywhere. So I have intentionally chosen cosine this time instead of sine, because just to show you that the results don't change. No? So what are the simplified equations now? No, dpk by dt is equal to apk bqk minus d1 k square pk and dqk by dt. dt is equal to c pk plus d d2 k square k. Okay, this is the new set of equations. These tell how the amplitudes of the kth mode for species 1 and species 2 change with time. Is everyone on board? I'll wait for 30 seconds before moving forward. So this should have been sufficient, by the way, for the step 4. But you could go in principle one more step, which is to write this in the form of matrix. D by dt. Now, unfortunately, I'm assuming that you are comfortable with the matrix, no, notation now. So, two-dimensional dynamical systems do require you to know this. Okay, where see, look at this now. What is the coefficient for pk? First term, a minus d1k square, right? A minus d1k square. This remains b, this remains c, d minus d2k square. Do you all agree with this? This is the matrix form, and this is the new Jacobian matrix. It's spatial perturbations, spatially homogeneous perturbations. Is everyone fine? So this was the what I was expecting you to do. I know that at least one group got up to this point, which is very well done, by the way. Is everyone with me so far? So I think, of course, I have assumed a few things in the mathematics here. I'm assuming that you know how to do matrix multiplication. You're comfortable using Taylor series and so on. Okay. Please do revise if you are not comfortable. But for those, for some of you for whom, if this is too much of mathematics, it's fine. You will learn something very beautiful. Hopefully, by the end of Monday's class, if not today's class, understand that concept. Focus on that concept. Okay. Even if the steps are very tedious. Okay, is everyone with me on the new Jacobian matrix? Okay, here is my question. So we started off under the premise, okay, that the homogeneous equilibrium n star is stable, right? So n star is stable. We wanted to know, address this question: is the mean field homogeneous equilibrium n star stable to heterogeneous perturbations? This is what we really need to answer. We know these two conditions. We know that a plus d is less than 0, ad minus bc is greater than 0. We already know this. Now, can you tell me, we have a new matrix now, jk. Will the eigenvalues of this new matrix, so if I want to rephrase the question, right? Rephrasing the stability question. What do we have? It's same as asking, are eigenvalues of JK, okay, both negative, okay, given that J had that features, given that A plus D was less than 0, this was given to us, right? And AD minus BC was greater than 0. Given these two are the eigenvalues of JK both negative. What do you think? Okay, before you answer, what do you think? Is the rephrasing of the question clear to everyone? Do you have any questions on this? Okay, so no questions. I'm assuming it's all clear. So what do you think? Can you tell me your intuitive guess? So so you remember that in the single species model, what did diffusion do? Diffusion homogenized, right? It was spreading things around. And remember that I had also shown you this diffusion equation solution from random walks, right? Of course, there was no reaction term there. How did the diffusion equation solution evolve? It basically started as a peak at a delta function peak at 0, and it basically spread out and became basically homogeneous. And in the end, at t as t tends to tended to infinity. And the same thing happened in the reaction diffusion system with one population, right? Whatever perturbation I made, it was basically homogenizing it. What do you think will happen with 2 dimensions? Do you expect the same intuition to hold true? There is a D1 that is homogenizing population N1. There is D2 that is homogenizing population N2. Okay. And you know that the original population was stable under the homogeneous conditions. What would your guess be? Yes, someone.
Like
Well, if you
they
already
should be
know the
negative.
answer, don't tell me. If you're thinking it for the first time, please answer. Yeah, go ahead.
So there are conditionality aspects related to
Sorry?
some of the values.
Mhm.
So for one particular condition, the eigenvalues turn out to be negative,
Mhm.
and the system decays out, the perturbations decays out.
Mhm.
So that actually is
Mhm.
the condition is actually
No, don't tell me
when
the conditions. Just I'm not asking you to give me an answer based on your calculation. I'm expecting an intuitive answer. If you had only species 1 with diffusion, it's going to homogenize, right? If you had only species 2 with diffusion, it's going to homogenize, right? Now the combination of 2 species has an homogeneous equilibrium. Okay. What do you think diffusion will do with 2 species? Now, what do you expect to do intuitively? Don't tell me based on the calculations, just intuitively. What's
There
your
might be a
intuition?
there might be a possibility that the populations oscillate.
Oscillate.
Yeah.
So although the oscillation is something okay interesting, but you assume that the the mean field equilibrium did not have oscillations. Let us assume that. Okay. Let us assume the mean field equilibrium was a this basic stable equilibrium. What do you think diffusion can create oscillations? Is that what you're saying?
Yeah, because like both are coupled to each other. Like if suppose there
But
might be
the
some.
mean field system did not have this property. Mean field system was just a simple fixed point. It's also called, what is it called? Um, stable node, I think, no? Yeah, something like a stable node. Do you think despite that it's possible to have oscillation? Okay, that's fine. Okay. Anybody else? What is your intuition? I mean, I'm asking only those who haven't done this before. Huh? If you already have done, you know the answer. Your answer will be less interesting to me in that sense. Okay. Anyway, so that's what you need to now find out. Okay. Naveen, you want to say something?
And I was just going to say that it's probably going to depend on the diffusion coefficients.
Okay.
Uh,
Why so?
So like if you perturb, so let's say that QK is QK. Let's consider the perturbation QK. So if D2 is more, then I think QK would have a greater impact on the stability, whether the perturbation is going to decay away or not. That's what I'm feeling intuitively anyway.
Okay. Think something about the diffusion rate might make a difference.
Yes,
Okay.
yes.
Okay, sounds good. No problem. So let's just figure. This is our. So we have learned. We have come this far. Let's now see what happens. Okay. So that comes to a step 5 that I want you to work on now. Okay. You know, you need to check if JK has same properties. Okay. What are those same properties? Trace of JK must be, if it is stable, what must happen? What must happen to trace of JK? It must be less than 0, right? Okay. And so what is trace of JK, by the way? Trace of JK is A plus D minus K square D1 plus D2. So this was negative. We knew this, right? From the mean field system. What is this? Is this negative too? Okay. So this with a minus sign, of course, this is negative. So therefore, so this condition holds true. Okay. So the trace of JK continues to be negative. Is that fine with everyone? So what's the second property that you have to check when you have for the equilibrium stability? Second property will be determinant of JK. What is that? That's going to be, product of these two diagonal terms minus PC. Okay, so you have A minus D1 K square, B minus D2 K square minus PC. We want this to be greater than 0, right? For stability. Is that right? So what does that simplify to? That becomes AD minus BC. AD minus BC, this term, and then you have this multiplied by this and this multiplied by this. Okay, they both come with a negative sign, and they both have this K square, and then you have AD2 plus DD1. Okay, and then you have product of these two, which is D1, D2, K power 4. We want this to be greater than 0. That's what we would like. Is that fine, everyone? Determinant of JK. But remember that this is already, we know this is positive. So these are the two terms that have been now added. Okay. And then we want to know if it is still positive, right? Now, what about this term? What about this term?
This is positive.
This is positive, right? Excellent. So this is positive. To a positive term, I am adding more positive terms. And what about this term? Is this positive or negative?
Can be either positive or negative, right?
Can be either. Why so? We already know one thing. Remember, we know that A plus D is negative, right? Can we use that in some way? A plus D is negative. does it mean with a question mark AD2 plus DD1 is negative? It's a question mark. I'm asking you.
Won't that depend on the strength of the diffusion coefficients?
Yeah.
Okay. So, why so?
I mean, if
Because
D1 and D2 are nearly equivalent, then you can just take them common, right? And that would also be negative.
Okay, so if D1, D2 are comparable, right? Okay. Assume D1, D2 are comparable, then what happens? D1 and D2 are comparable, okay? And let's call them D. What happens? This term then becomes, AD2 plus DD1 is basically D times A plus D, which is negative, which means this is negative, and negative with a negative becomes positive. Then therefore the entire determinant will be positive, right? So in such a case, determinant of JK will be positive. This means that mean field equilibrium is. Do you all agree with this? Basically, if D1 and D2 are comparable, the two diffusion rates are comparable, the mean field, what am I saying? Mean field equilibrium is stable. Stable to heterogeneous perturbations. Do you agree with this? So somebody made a very interesting observation that two
So
different
the stability can include stable oscillations also, right?
So basically, let us think about the following way. There was some stable structure before. Will that remain same after the introduction of diffusion? That is the question I'm asking. Now, whatever the structure you gave me as stable, that could be whatever it is, will that remain stable? That's the question. Now, the question is now, are oscillations considered stable equilibrium? Then that becomes a question, no? Can you tell me if are the oscillations considered stable equilibrium?
Maybe for a particular amplitude.
Huh?
For some amplitude.
So now go back to the following. Go back to the original Jacobian. What will be the two eigenvalues if you have a stable oscillation in the mean field model? If you have a stable oscillation, what will be
sustained oscillations, the trace. For sustained oscillations, the trace should be equal to 0, right?
That's for circles, no?
Yeah, sustained oscillations for both N1 and N2. I think. Yeah. Okay. Yeah. Circles.
Means if it is indeed true, what you are saying, the eigenvalues are not less than 0, right?
Right. Right.
So, do you know of any case when you can get a stable oscillation with eigenvalues negative? So the answer, I think, I have to revise myself this. I think the answer is no. So stable oscillation means that one of the eigenvalues are positive. Okay. So therefore, we're not really working with oscillation, but you can have a stable spiral. Okay. So you could start with a stable spiral, which meets these conditions. And then we are asking what happens with diffusion. Does that answer your question? We were asked this question.
Yeah.
Okay. So initial system we are starting with doesn't contain oscillations. It can have stable spirals. Okay. Okay, now, so here we are. So we have shown that if the two diffusions are comparable, the mean field equilibrium stability continues to hold true. What if they were not same? What if D1, D2 were dramatically different? Then could you still make the same statement? And if so, why not? Okay, so let me take the next step forward. So basically, as you can see, this is positive. This is positive. The only way you can change the stability is by having the middle term have a very large negative term. What happens in such a case? If this happens, this with the middle term, which includes a negative sign, if this becomes very largely negative, so that the total term becomes negative, then what happens to the stability? The stability goes away, right? Okay. So now if this term has to be negative, what should this term alone? AD2 plus DD1 must be, it must have the sign of, the minimum necessary condition is what?
It should be positive.
Should be positive, no? For for determinant JK to be less than negative, that is stability to break in spatial system. What do we need to have? We need to have necessary condition is A D2 plus D D1 must be positive. Okay. Let me also do one thing. Let's assume that D1 is D, okay, and D2 is 1. Okay. What does that mean? This means that AD plus D must be greater than 0. Just what I have done is, I've arbitrarily set one of the diffusion constant to be 1, and then I have written it down in this formula. Okay. So this has to be true. Okay, now here is, okay, so when is this true, by the way? We know that A plus D has to be greater than 0, right? And what about the signs of A and D that we don't know? Do we know? That we actually don't know as of now. Okay, so I can sort of arbitrarily assume that, assume without loss of generality that A is positive and D is negative. Why am I considering this? If A and D were both negative, then this would not be true anyway. Okay, so let's assume this, meaning A is positive, D is negative. If that is the case, what should D be? Okay, if this means that D must be necessarily greater than 1. Okay, if D was indeed 1, then again you will have A plus D, which will be negative. So we want a positive term to dominate. So therefore, we necessarily have D greater than 1. Okay. Okay, which means that one species must necessarily diffuse faster than other species. Is that clear to everyone?
This is a necessary condition, but not sufficient, right?
Absolutely. This doesn't guarantee that the stability will be still broken. It's a necessary condition. Okay. And in fact, just think about the following. So A is greater than, again, this is a necessary condition, another necessary condition, right? Also a necessary condition. They must have opposite properties when they're on their own. Isn't this very interesting? A on what exactly is A, by the way? Think about it. If only species N1 was present, A represents the linear stability analysis coefficient of the species 1, right? Okay, only species 1 was present. A greater than 0 means that, it actually is a, I don't know, how clear this point is. I want you to think about whatever I'm saying. It's going to take some time because these are fairly intricate points. So let us again go back to the, mean field system. If we had a mean field system, if you write down how the perturbations change, you had something like this, right? A, B, C, D, N1, N2. Oh. Okay, A, N1. Okay, this is what we had. Consider only one species being present, okay? Only N1 is present. Then what happens? You have N1 dot is equal to A N1, right? Okay, since A is positive, what does that mean? N1 grows on its own. So we call them autocatalytic, okay? So N1 is present on its own. They call them autocatalytic, meaning, if you deviate N1 from its equilibrium, it actually grows further. What about N2? Meaning I made a perturbation only in the second species. N2 dot will be dN2. Since D is less than 0, what do we get? What do we have? N2 decays. Is that right? So N2 basically.
For A greater than 0, it just means that with respect to N1's own population size, N1's stability.
So you are at the equilibrium. You are at the equilibrium. I have made a perturbation only in N1. That's what I meant.
Yeah, so it's sort of like unstable with respect to N1, right? That's what A1
if I made only perturbation to itself, it will go away from the equilibrium. It doesn't mean it's unstable.
So it can go in either directions, right? If A is greater than 0. As in, if I decrease N1 by a little, then it can also decrease, right, the population size.
Can you just repeat your statement?
So when I'm saying A is greater than 0, so that means that the stability is unstable with respect to N1, right?
It doesn't mean it's unstable because stability determined by the eigenvalues entirely, not just A. Okay, so what happens is when you make a perturbation only in the N1 dot is A N1, right? So N1 that perturbation grows, but N2 dot is C N1. Okay, but depending on the sign of C, N2 will also increase or decrease. And the moment that happens, all the 4 terms now become important.
Okay, right.
And then perturbation eventually decays because that's what we started off with, right?
Right.
Okay, but I'm just telling only if you initial growth is what we're talking about. Okay. On the other hand, for the N2, what happens? N2 decays, we call them inhibitory. Okay, inhibitory. Okay, so this is again necessary condition. So if one of them is autocatalytic, other one is inhibitory, then there is a possibility that the mean field homogeneous equilibrium might become unstable. Another condition was that D was greater than. What was this D, by the way? Was this D1 or D2? Oh, I think I messed up, huh?
D1.
Oh, but I have these two equations are not consistent. Sorry. I have said D1 is D and D2 is equal to 1, but what I wrote was something exactly opposite, huh? Right? He is great. Okay, I should then maybe swap the definitions, huh? So I'll still keep this maybe AD. No. I'll so I can write this as A plus DD. Okay. A greater than 0, D less than 0. Okay. And now I think the D just swaps, right? Is that correct? Can everyone confirm, please?
Yes.
Okay. Okay. I have a feeling I may have made a mistake, but it's fine. We'll find out if when something goes. Okay, now tell me which one is moving fast, autocatalytic catalytic species or the inhibitory species? D less than D was basically the autocatalytic, D was the diffusion coefficient of the species 1, autocatalytic species, no? Right? So D less than 1, what does it mean? I think I should actually do the following. I should just note, I should not change the D1 at all. I should just send D2 to 1, D2 to 1. That just makes life easy. D1 is less than 1. What is D1? D1 is the diffusion of autocatalytic species. Okay, another interpretation is D1, meaning autocatalytic species must move fast or slow? Slow, right? Conversely, inhibitory species must move fast. Is that fine? Are you all happy with these interpretations that I've been giving you? These are all necessary conditions. Are they sufficient? What is the sufficient condition? Sufficient condition is, go back to the determinant. This must be negative. Is that fine? These are all necessary, but they are not sufficient. So you need to now find the conditions under which this actually becomes feasible. Okay, that now requires some additional algebra. Let's call them step 6. So now let's denote the determinant of JK as dk square, I think d1k square minus k square. Just check what we had. K square a plus dd. Oh, this is k4, sorry. Plus AD minus BC. Okay. So this is what you have. Is it fine? Where am I? Sorry. Okay. Okay, AD minus BC. Okay. So what you now need to find is, what is the sufficient condition? So this I will leave it as an exercise for you. It's a bit of algebra. I can again give you steps, sub-steps you have to do to arrive at this. So basically, this is that. What is this, by the way? This is that. If I set k square is equal to some new variable, let's call them x. This basically becomes a quadratic equation, right? So this is basically using the solutions of quadratic equation and show that one of the solutions is positive, whereas the other solution is negative. Whatever the conditions that entails will be answered to this question also. Okay. So I want you to think about this, and hint basically is that of quadratic equations. So I will, I will leave that as an exercise for you. Now you have some things remaining, right, in your, steps for the lab work today. So well, let me tell you the answer. By the way, it is indeed possible. Okay, it is indeed possible that to find conditions under which determinant does become positive and does become negative, which basically means that this mean field homogeneous equilibrium can, under some conditions, can become unstable to heterogeneous perturbation. So it is indeed possible when you have two species, as some of you have guessed. So what is tell me what is somewhat counterintuitive about this? Why is this such a big deal? Why should this be a big deal at all, if at all? So we had a mean field solution, right? And the moment you added diffusion to both of them, and under some conditions, we can mathematically show that those mean field solutions can become unstable. So what is the big deal about this? Why is it interesting? Forget about the biological implications, but just from a purely sort of intuitive perspective, why is it interesting?
So one question that also arises is where it would go then if the homogeneous equilibrium themselves become unstable.
What's the final stable state? No, that's one question you have. So we have lost our equilibrium solution. So what happens now, right? So where will perturbation go to, right? That's one question. Okay, very good question. What else?
Like, are there other equilibrium solutions for the diffusion equation? Maybe.
Okay, are there other? Okay, that's fine. Okay. What else? And on what are the nature of those equilibrium solutions, right? Are they again homogeneous? Do they have how will they look like, right? How will those look like? So it's a bit of a mystery. Actually, appears quite mysterious. Yeah, go ahead. Yeah, tell me.
So it's like so in bifurcation, as the equilibrium comes out of the blue sky, so it is also the case over here. The new equilibrium.
Yeah, it's something like a bifurcation, right? The mean field solution goes away, but something like, you're right, it's absolutely like a bifurcation. We had this simple models like logistic discrete model, right? We had some simple solution like a stable equilibrium. Suddenly cycles came out of nowhere, right? And then likewise in two species also, although we did not cover this, there also we found suddenly cycles. So maybe something like that might be happening. Okay. What else? What would be the analogous of cycles in space? What would be analogous of cycles? If you have temporal cyclic behavior, what would be the analogous of spatial?
Patchiness?
Yeah, something like, periodicity, right? Periodicity in space now, right? Yeah, that's a possibility. Okay. What else can happen? Okay, so why is this somewhat counterintuitive is the following. Diffusion is expected to homogenize, right? But the moment you have, but the fact that diffusion can actually maintain heterogeneity is a huge surprise, isn't it? So when we think of diffusion, for example, think of ink being dropped in a cup, right? Slowly things diffuse, or any simple diffusion process you can, simple diffusion you can think of. We always think of, diffusion as homogenizing, right? But the fact that diffusion can somehow make heterogeneity, actually can enhance heterogeneity, is very counterintuitive. Okay. So in simplest terms, this is actually very counterintuitive. That diffusion, how can diffusion make things heterogeneous? It's always supposed to make homogeneous, right? So that's what makes this problem mathematically and from physics point of view very interesting. Okay.
Sir, it's the reaction term that brings in the heterogeneity, right?
It's a combination. You know that the reaction alone cannot, no, because if I said D1 is equal to D2, I cannot, right?
Yes.
It's not reaction alone, it's not diffusion alone, it's combination, it's a reaction diffusion equation. Okay, it's a combination that makes it, that makes heterogeneity possible. Okay, we still don't know what happens in the end, by the way, we haven't figured that out. All that we are saying is a heterogeneous perturbation, now we have convinced ourselves, at least intuitively from these equations, that heterogeneity can blow up, even with diffusion being the underlying process, right? Even when the homogeneous solution was stable in the mean field system. That's what we have now convinced ourselves as a possibility. Okay, but we don't still know what happens to it. Maybe it will initially blow up and something else might happen. We don't know. We still haven't figured out. Okay, we will eventually figure that out. So there's another point I want to say, just forgot. Okay. So there's another, if it is indeed possible that, heterogeneity in space can be maintained by diffusion, it has really interesting, interesting implications, right? The moment, if you see heterogeneous patterns in nature, right? What is your typical assumption? What would be your basic assumption about the underlying processes? We often attribute it to, sorry?
So mechanism might be different. We generally
we often attribute it to maybe an underlying heterogeneity, right? Underlying spatial heterogeneity. That would be, it's similar to sort of, similar to the idea that when you see cyclical behavior in nature, we are likely to attribute it to a seasonal feature, right? Or something that is temporally varying as a driver, right? So we know that that was not true. It could, we now know that temporal heterogeneity, which is cyclic behavior, for example, could arise entirely in systems that are whose processes are homogeneous. So likewise, if we see a spatially heterogeneous pattern in nature, we often attribute it to underlying spatial heterogeneity, but this is not necessary. It can even arise a diffusive process. Okay, so that's the biological, implication of, the fact that diffusion can, make things unstable. Okay, so I will stop here today. What I would like you to do for your submission is the following. You don't have to do any new calculations. Whatever I have, the step 1 to 4, write them down clearly, especially these parts, do it on your own. Okay, try to see on your own if you want to modify a little bit, but even if you just reproduce, it's totally fine, because I want you to feel comfortable in being able to do this. Okay, and then I want you to just basically reproduce to a large part all the arguments we have made, especially what is a necessary condition Okay, what is the necessary condition to have, at least in principle, where heterogeneous perturbations can, become unstable? So I have already explained all of those to you, but think through on your own and reproduce this on your own and in your report today. Okay. The reason why I'm saying this is actually very counterintuitive. It has very interesting features also. I will cover the rest of it on Monday. Is that fine? But I would like you to submit before tomorrow. I won't give an extension this time. Okay, because I've done everything for you. And optionally, for those of you who are mathematically inclined, please also derive the sufficient condition. Okay. So let me just write down the lab assignment for today. Lab assignment. So if you did not, please complete steps 1 to 4. Okay. Derive necessary condition for instability with the diffusion. Okay. And verbally describe the conditions. And then finally, it's optional. Derive the sufficient conditions for instability. Instability and interpret them. Is that clear to everyone? Any questions? Have I shared my screen?
Yes.
Okay. So if there are no questions, in all leave, I will create the assignment for the team. Okay. But please submit by tomorrow.
I had a question about the biased diffusion that we had done like a few classes ago, but so I don't know if I should ask it now or
what is the
biased email or something.
Sorry?
I mean, it was you gave us an assignment about 2 lab assignments ago.
The random walk.
Where you, the random walk, where you said derive the diffusion equation, but if the random walk was biased.
Yeah, right. Oh, there were a couple of clarifications I wanted to actually say about that. Yeah, I'm happy to do that. So what's your question?
My question was, in the unbiased case, we argued that since the MSD is proportional to time, x square by tau, x square by t in the limit will be a constant, right?
Yeah, I can guess your question. Continue, yes.
My question is that in the biased case, this is not true. MSD is not proportional to t. It's proportional to t square.
Yeah. So it's a thing, to be very honest, I don't fully understand. So when we derive let me just share the screen and make this point. Let me tell you what I understand, what I don't understand. If any of you understand, please let me know. Okay. So I think Shikhara's question is as follows. So we had an unbiased random walk, right?
Your screen is not shared.
Oh, okay. Sorry about that. Unbiased.
Yes, we can see it.
So after this, I will also like to discuss why Abhip Shah's code was better than mine, and if any of you figured out why. Okay. Okay, unbiased random walk, we know the definitions, I won't repeat that. We derived the following, right? We said that dpx by dt, we got this diffusion equation. D dou square p by dou x square, where d was written as delta x square by 2 delta t, where both delta x and delta t goes to 0. Okay, and then we said, we motivate this by the fact that in random walk, delta x square is proportional to delta t. Okay, but I want to clarify one thing here. I'm actually not substituting, I'm not substituting this, in the, we're not substituting this in the derivation, by the way, because that requires an average here. We're not doing any of it. We are being inspired by this to define this as a constant. Okay, that's the first point. Now, if you now do biased random walk, again, the definitions I have covered, so I won't do it again. So the diffusion equation that's expected is as follows: minus v dou p by dou x plus d dou t square by dou x square, where v is limit of p minus. Okay, and d is limit. Is that right, people? Is that what you all found?
Oh, yes.
Okay, so again, delta x goes to 0, delta t goes to 0, delta x goes to 0, delta t goes to 0. So here is the sort of problematic issue here. Okay, so there I happily said I inspire and do this, but as Shekara pointed out, this is not true anymore when you have a biased random walk, right? So this equation, when we do this in the limit. So let's forget about what we know about the mean square displacement entirely. Okay, now first of all, these two cannot be simultaneously true, right? Delta x square by delta t, if that is a constant, then can delta x by delta t be constant? Right? Only if this is a constant, or let's look at the other way around. If delta x by delta t was a constant, what happens to delta x square by delta t in the limit? This will go to 0, right? So you see the problem, right? If we assume this to be a constant, this goes to 0. If we assume this to be a constant, this blows up. Okay, so we have a problem. So what people do is that this is done in this limit. So you're actually very close to basically an unbiased random walk. Okay, so the way the diffusion limit is still true. Okay, but so is drift by, but in the limit p goes to 15. Okay. This is my understanding of how you derive the drift diffusion equation for the biased random walk. Does that help you clarify your doubts, Shikara?
So the assumption is still the second one, because
so
delta
the
x
diffusion
square by
assumption,
right, but the diffusion assumption is no longer motivated by what we knew from our MSDs, from our random walks, right?
Both of them are not motivated by it, except that we are looking at close enough to the unbiased random walk, and therefore they are probably okay.
Okay,
that's one way to think about this. Okay, but maybe there is a better answer. If any of you know, let me know.
All right, thank you.
Okay, now that's about this one. So another point, which is some of you said that if you use my code, okay, and calculate the mean square exponent for the power law, you did not find the pattern That was expected, right? Is that right?
Yes.
Okay. So I think the reason is following, because I wrote an extremely sloppy code and I was hoping it will still be okay. So in my mean square displacement code, so let's say an animal has moved like this, okay? Because the end point is the starting point, okay? Let's say I'm looking at a lag of 3. Okay, so the mean, what is the mean square displacement at lag 3? How do I compute that? What I do is I take x4 minus x1, right, whole square, and then I take x5 minus x2 whole square, and then I take x6 minus x3 whole square, and I take all such things xn minus 3 whole square, and then I divide by the number of such instances. Okay, divide by whatever n. Is that fine? That's what I do. Horrible, sorry, really horrible writing. Really sorry about that. This is what I am doing. And now what Abhiprash's code does is the following. For the same lag, what she does is effectively, she doesn't do it exactly the same way. Effectively, what she does is this. And then divide by the number of such whatever instances. Now tell me which is a more accurate way of doing it. Which is the right way of estimating MSD for lag 3?
The second one.
Why use the first one? Not good.
Because the first one you're having sort of overlapping
exactly.
windows, right? So they're not independent.
Absolutely. So x4 minus x1 is not independent of x5 minus x2. So I did not think it will make such a huge difference, but it seems to make a huge difference. It seems to fully kill the pattern. Huh? So that's the reason why. And also, of course, she was using a lot of replicates. But I think this is the reason.
Sorry, I didn't quite understand why they're not independent. I mean, at each time step, the movement is going to be independent. Right?
True, but each time step is fine. But x4 minus x1 has the information of the jump between 4 and 1, right?
Yeah.
x5 minus x2 has the information of jump from 5 to 2. That information, there is a commonality between these two now, right?
Okay.
2 to 3 to 4 is common to in both of these.
Okay.
And likewise, same here. Huh? So that seems to make I thought that if we had long enough time series, maybe that doesn't matter, but it clearly matters. Is it clear to everyone? So, but what I still don't understand fully is, why is that reducing the exponent to 1? What's the logic? I mean, maybe basically it's now like a correlated MSD, not really independent sampling of MSDs. So maybe there must be some way to show that this doesn't really converge to the right exponent. Is that clear to everyone?
Yes.
Okay, great. This, let me tell you very honest, I had never done this calculation myself before. So in this course, I often give questions which I myself have never solved. So it's always good to clear my own small misconceptions here and there. Thanks to, I don't know if anybody else did the Abhiprash's way, but I think, certainly thanks to her for doing it correctly. And I myself had never seen that, pattern of exponent versus power law exponent before. So it was, I expected that to be true, and I get the assignment. I actually don't know any place where that graph exists in any book or any other place. So it was good to see in the assignment. Okay, cool. So we're done for today. So I'll see you on Monday again. Bye.